All right. So welcome to the our next lecture, lecture 6. So last time we discussed this introduction to quantum physics. We discussed these general principles of quantum mechanics that lie in the center of the quantum computing. And today, finally, we will be starting applying these concepts to the quantum computing and quantum algorithms. So our goal for today's lecture is to discuss the elements of quantum circuits, and we will be starting with single qubit operations first, and then the the next lecture will be dedicated to two qubit operations and simulating uh, realistic quantum quantum circuits. Yeah, so as usual, let us start with importing these libraries. Um, Probably we will not use them much today. Uh, yeah, so starting talking about quantum circuits, it is instructive to kind of go really quick through the principles of classical circuits. Uh, so from the very beginning, I know that I'm not the computer scientist, right? I'm rather physicist and electrical engineering, electrical engineer. So here I just put some very very brief introduction to classical circuits. So you of course know that classical electronic computers are based on uh, uh, transistors, right? So some nonlinear uh, electronic devices that allow to control current or voltage drop across some resistors, for example. Right. So when this transistor is open, the voltage is low, then even it's closed, the voltage is high. So we operate with zeros and ones. And it's not enough to just take billions of transistors and put them together. We need to go on the next level step uh, of this architecture, right? So we group several transistors together to create uh, some basic logic gates. Okay, so each logic gate consists of a number of transistors, and we just group them to form these logic elements, and then we build the um, classical computing based on these logic elements. Um, so here are some examples of traditional classical logic gates. Uh, in order to create any classical algorithm, you don't need all of them, you just need some, 3 or 4, because some of them um, can be expressed as the combination of others. Right. So the gate that uh, maybe the easiest one, and also that finds its place and also in quantum, is not gate, which basically just flips the the bit, right? So if you get 0 in input, it flips it to the to 1, and if you get 1, it flips it to 0. So not gate can be just a simple transistor with a resistor. So when you apply 0, the transistor is closed, and then the voltage drop is high, and then when you open it, it turns it to 0, something like this. So we, just like any other logic element, we can express all these rules in form of truth table, right? Which suggests how this logic element behaves. So this is example of single input logic element, not gate. So you get one input, one output. It's not enough to create a universal classical algorithm using just one input gate. You need something else. So you need more. You need to be able to like control uh, inputs and outputs depending on well, different inputs. Okay, so for this reason we introduce a new one which is called XOR gate. So you see this one gets two inputs and one output. So like for example, if input 0 0, then the output is 0, and if then input is 0 1, then output is 1. 1 0 is also 1, and 1 1 is 0. So basically you can consider this gate as a one signal and another one control. So like you get signal, and then if control is 0, it leaves this signal unchanged, and if control is 1, it flips the signal input. Right. So summarizing all these rules in the truth table, we get this. So two inputs, one output. Important point to notice here is that this XOR gate is irreversible, because let's say you measure in output like 0, then you still have this uncertainty whether it was 0 0 in input or 1 1 in input, right? The same for 1, you get 0 1 or 1 0, so you kind of lose information. In physics there is a fundamental theorem that connects this losing of information and losses. Okay, so if your gate lose information, it leads to increase this entropy, and as a result, turning some energy into heat. For this reason, some uh, computer scientists back in time when this logic just started developing, some of them thought that maybe we won't have classical computers power enough, because if these gates are dissipative, then like fundamentally dissipating, unavoidably dissipating, then we would never have a powerful enough classical computer. In fact, we can make this gate reversible. We just need to add XOR. So you just need to add another output to get two outputs, and then your gate will be reversible. So you can avoid that. In quantum, we discussed last time, right? In quantum, we have similar situation. We require any quantum circuit to be executable in both directions, like from left to right, from right to left. The circuits must be reversible, time reversible. Only time reversible circuits can be considered as lossless, and this point of loss energy and information is much more critical in quantum comparing to to classical, for the reasons that we will discuss in what follows. So for this reason, any computation in quantum circuits described by unitary transformations, unitary operators. Just to remind you that unitary transformation is obeys uh, this requirement, right? Then operator Dagger operator must be equal to identity operator, or equivalently, the operator must be equal to the or operator Dagger must be equal to operator reversed operator u to the power of minus 1. So let us let us look at the typical quantum circuit. I took this one from this paper. So here you can see a quantum circuit consisting of 5 qubits. Okay, so traditionally we number the qubits starting from 0. So 0, 1, 2, 3, 4. So it's a 5 qubit system. And then each qubit kind of represented by a line, like horizontal line. And then these elements in rectangle and elements like these represent quantum gates. Okay, so something that manipulate with the state of a qubit. These operations are set or arranged in layers, starting from layer 1, layer 2, layer 3, 4, 5, and so on. So in drastic contrast to classical computers and classical algorithms, where we deal with currents, right, that run over some wires, transistors, and so on. Here, so this classical circuit, this classical electronic circuit is kind of circuit in space. So you really draw the circuit over some some substrate, right? You use this CMOS technology to layer the circuits and so on. Here, this circuit, this quantum circuit, is or can be called temporal. Okay, so all these operations happen in time rather than in space. So you have sitting still qubits. In this case, it's 5 qubits. This qubit is something physically presented like a piece of circuit or some quantum dot or something else that exhibit the quantum properties. And then we apply the different stimuli, okay, some pulses of current or of electromagnetic field to these qubits in particular time instance. So each layer corresponds to different time instant. In layer 1, we apply some pulses to qubit 1 and qubit 0, qubit 3. Then in layer 2, we do something else. Then layer 3, we do something else to this particular qubits. Okay, so these actions happen in time rather than in space. So this is a big difference. Of course, there are different approaches to quantum computing. One, which I just described, is so-called microwave quantum circuit-based quantum computing, where the qubits are given by some pieces of circuit. We will discuss them in later. There are other types, other approaches to quantum computing, for example, photonics, in which we have photons that run over some optical circuit, like some laser beams and so on. So in that case, this photonic quantum circuit is more kind of space computing. But traditional microwave quantum circuit-based computing is rather temporal. All right, so and by the way, what is not demonstrated here, but must be present in any quantum computation, is the last layer of measurement. So it's going to be some layer of measuring gates. And of course, since this measurement, as we discussed last time, is non-reversible, right? When you measure quantum, you destroy quantum state, you collapse the wave function to one of the particular possible states. And this is, of course, not time reversible. So when we're talking about these unitary transformations, operations, we mean this part before the measurement. All right. So now our goal is to discuss single qubit gates. Single qubit gate means that we manipulate with a single qubit, leaving other qubits untouched, right? So for this goal, it is instructive to represent this state of a single qubit using the block sphere approach, right? We already discussed this one several times, but now I would like to make it more well, rigorous and filled with theoretical and the information, whatever. So block sphere is a unit sphere, meaning that its radius is equal to 1, the magnitude of the radius. And the purpose of this sphere is to represent any state of a qubit, which is superposition of two terms, right, of state 0 and state 1, with different complex valued probability amplitudes. So let us now rewrite this state in a different form that will allow us to represent this state in a over block sphere, right? So block sphere is a three-dimensional object. Since we fix this radius to be equal to 1, so any point over the sphere is given by two coordinates, theta and phi, just like any coordinate on the Earth, right? We need two coordinates. So let us rewrite this for this general quantum state of a qubit. We notice that C0, C1 are complex valued, right? And we can assume that C0 is a real valued and C1 gets this general complex valued shape. Why? Because it is just up to the relative phase between these two zeros, C0, C1. If you write C0 also in this form, C capital 0, then e to the power of I, some another phi. So basically, you just can factor out this common phase difference. So you make the first term C0 real valued and C1 will be given by this. So phi here is the relative phase between two states. And of course, these two coefficients must be normalized. This is the normalization factor. Otherwise, we wouldn't be able to consider them as probability amplitude. So they must be normalized to qubit. Okay, which leads to this one. And now, using this this assumption, we can rewrite this normalization factor in this form. So now it's a combination of two real valued functions, right? And using this trigonometrical equation, we can rewrite this in in this form here, assuming that C0 is a cosine theta over 2 and C capital 1 is sine theta over 2. So theta is a spherical angle. Okay, so we substitute this phi0 C1 here, and also recall that the C1 is multiplied by this exponential function. So this exponential function appears here in this formula. So this is essentially the same state as this one, but rewritten in terms of basically other coordinates, theta and phi. So this theta and phi can be considered as spherical coordinates over this block sphere. So phi runs from 0 to 2 pi and theta from 0 to pi, as just like traditional spherical coordinates. To call for block sphere, as before, we use this Qiskit visualization, plot block vector, import it, and call for this function. The result is this one, right? So it's a red arrow that indicates the quantum state and yeah, block sphere. So there are several let us say fundamental states on this sphere that we need to discuss in more detail. To do so, let us rewrite this formula here using the Euler's formula for the exponential function, right? So this is the very well known Euler's formula for the exponential function. So you can express this exponential function with the imaginary unit here as a sum of two cosine and sine must be multiplied by imaginary unit, right? So this function complex, this potential exponential function gets a real part and imaginary part. Real part is a cosine and the imaginary part is sine. So we substitute this formula here and get this general state. Very useful and instructive in terms of we can now substitute this theta and phi different values and figure out which point on this sphere corresponds to which state. So we've got three pairs of fundamental states. One pair of fundamental state is state 0 and state 1. So by default, you can see them here, 0 state, state 1. So state 0 in Qiskit, right, it's a north pole of this block sphere. State 1 is the south pole of this block sphere. So let us check that. Let us substitute. So for example, so you remember this theta, this angle theta is the angle between this line from north to south pole, right? This vertical line, and the angle, this the vector state. Like for example, if I put here 0 and here supposed to be, so it's a spherical coordinate should be 0 too, right? So state theta 0 phi 0 corresponds to this state 0. What is given here? Let us check that theta pi oops, np pi and gives you state 1. Okay, so theta pi and whatever phi gives you state 1. And this state 0 and state 1 are nothing but this state 0 and state 1. Okay, so this general qubit state given by this composition of state 0, state 1 with different probability amplitudes is just a combination of orientation of vertical orientation of this arrow and upwards and downwards orientation of this arrow. Second pair of fundamental states, also known as plus state and minus state. So the plus state is the state that corresponds to theta pi over 2 and phi equals to 0. So if you substitute pi over 2 here, recall cosine pi over 2, which is cosine pi over 4. Cosine pi over 4 is equal to square root of 2 over 2, right? So this one turns into square root of 2 over 2. Then this one also square root of 2 over 2. And then this one equals to 1 if phi equal to 0, because cosine 0 is equal to 1 and sine 0 is equal to 0. So you get this formula here. So everything simplified to 1 over square root of 2, and then just sum of these two, state 0, state 1. Similarly, for the state 1, for the state minus, the theta is the same, but phi is equal to pi, right? So if cosine pi equals to minus 1, right, and sine pi is equal to 0, so you get 1 over square root of 2, 0, minus 1. So these two states on the block sphere, it corresponds to states on these points at the axis x, right? This state is plus state, that one, the opposite is state minus. So in other words, this state is a superposition. We call this perfect superposition because this state get the same amplitude, 1 over square root of 2. It's a perfect balanced superposition of state 0, state 1. Just like this one, but they differ in terms of this sign, which is equivalent to some phase shift. Okay. This is the second important pair of states, and the last one plus I minus I. So again, using these values for these states, you can find out that this third pair are located at the axis y. This one, this positive direction of y, is equal to plus I, another one is minus I, and their formulas are given by this. So it's a 0 state plus I, which is imaginary unit state 1, and minus state is 0 minus I. Right, so so 3 pairs of fundamental states form the block sphere. Let us now start considering the single qubit gates. Do you have any questions so far? Don't hesitate if you got any questions or don't understand something. All right. So single qubit gates in quantum computing. uh, there are not that many single qubit gates. The 3 most important we already discussed. They are Pauli gates, Pauli matrices. You remember Pauli X, Pauli Y, Pauli Z. They are all particular examples of single qubit gates. Okay, so X gate. Sometimes we draw them using this rectangle with capital X in it, but more often it is given by this circle with plus inside. And mathematically, it is presented by Pauli X matrix 0, 1, 1, 0. Right. So, yeah, in matrix representation, it's given by this matrix. And let us check what happens when we apply when we apply this matrix to the state 0. So direct calculation leads to the result state 1. Similarly, applying to the state 1, it returns state 0. And in general, if you apply this gate to the superposition alpha 0, beta 1, you will get alpha 1, beta 0. So you basically just flip the qubit. Okay, so if initially your qubit was in the state 1, after applying X gate, you will find your system in the state 0. So it flips the qubit. This is similar to what we saw in the case of NOT gate in the classical computing. Very important, very important point how the two differ. In classical computing, you have one well-defined level of voltage inside or at the input, and well-defined voltage at the output. Okay, so your gate modifies only very well defined state of voltage, let's say. Here in quantum, the input exists in both opportunities like simultaneously. So this is your input, and you don't know in which state your qubit is given, 0 or state 1. What you can only say is the probability to find this qubit in either state. And the quantum gate is applied to both of them simultaneously, okay, and returns the result also simultaneously. It's like the gate that conducts this operation to these two possible states in the same time. Okay, so this is like an example of what is called quantum parallelism. So you don't know in which state your qubit is initially. You have to consider it in both states simultaneously, you apply gate that changes both uh, opportunities at the same time and returns you both results at the same time too. Okay, so this kind of well, you speed up your, it's not computation but the action of this qubit by kind of twice, right, by a factor of 2. Similarly, Y gate, another example, schematically is given by this rectangle with capital Y. This is the matrix. Compare it with the Pauli matrix. It is exactly Pauli Y matrix. Applying this this matrix to the state 0 returns 1 with imaginary unit, to the 1 imaginary unit with minus, and applying to the general state like this returns this output. Effectively, just like X gate, which is flip across the axis X, right? So this is axis X, and what qubit flip gate does is simply rotates this arrow around the axis X. Similarly, for the Pauli gate Y, it rotates this arrow around Y axis. So you get this result. And finally, Z gate or Pauli Z gate. This is the schematic presentation, very similar to what we saw previously. This is the matrix. Indeed, this is Pauli Z matrix. And when we apply this Pauli matrix to the state 0, it returns 0. When it applies to the state 1, it returns -1. Why? Because essentially it is rotation around axis Z, which is this vertical axis. Okay, so if it was initially 0, if you rotate this arrow or rotate this block sphere, nothing changes. So you, from starting from 0, you return to 0. And if you were in the state 1, this transformation returns this minus, which doesn't change the probability because the probability is the square of this coefficient, and -1 to the square is equal to 1. All right, so this is about X, Y, and Z gates. Maybe more important, well, more important gate is called Hadamard gate. So the Hadamard gate is the gate represented by this rectangle with H capital in it, and given by this matrix 1 over square root of 2, 1, 1, 1, minus 1. So you can, from this structure of this matrix, you already can see what happens, right? What actually happens if you apply this operator to the state 0? This is the state it returns. State 0 plus state 1 over square root of 2. So it's a superposition of two states. You started from state 0, you ended in the perfect balance superposition of state 0 and 1. With appropriate normalization, 1 over square root of 2, which is given by this prefactor here. If you act this Hadamard gate on the state 1, you get the same, but up to this sign, state 0 minus state 1. Again, it's a perfect balance superposition, but with the different phase. Similarly, if applying this gate to the general initial quantum state, this is the result. So in general case, you get the superposition of two states. From this, by the way, it's clearly seen that if alpha and beta are equal, so if you started from balanced state, right? In response, you will get on the state 0. So if in input you get superposition, perfect balance superposition, in the output you get state 0 or state 1, depending on the sign of alpha and beta. So important point, Hadamard gate creates quantum superposition. In fact, almost any quantum algorithm starts from creating all qubits in the superposition of state 0 and state 1. Okay, so usually when you like turn your quantum computer on, all the gates are initially in the state 0, which is essentially the ground state. You know that everything tends to the ground state, to the stable state in the in the in the equilibrium, right? That's why everything is 0, and then you need to put all the qubits in the superposition. So almost any quantum circuit starts from creating the superposition. I'm not sure if this one, yeah, like here, for example. So you can see that this layer 1 returns this qubit 0 and qubit 3. It creates the superposition of this one and this one. And then we also apply this Hadamard to the first qubit, to the fourth qubit, and so on. So you can see that this Hadamard gate is like very much used even in this simple circuit, already a few of them. So Hadamard gate creates the superposition. And finally, some other popular single qubit gates, starting from P gate, or also known as phase gate. So it's just the gate that acts on a state 0 and returns unchanged state 0, but if it acts on the state 1, it returns 1 with additional phase. Okay, so it changes the phase of the state 1, and for the general state in input, it returns the same state, but slightly changes the state of the state 1 phase. It changes phase of the state 1. Okay, you know that phase controls the interference. Why it's so important? Because P gate can create destructive interference or constructive interference, depending on this this phase phi. Okay, so let us again return to this example. Well, we don't have the P gate here. We have the another types of phase gates. This T gate here, here. This T gate also changes the phase, and the purpose of these gates is to balance or change the relative phase between different qubits to create constructive interference for the right answer and destructive interference for the other possibilities. We will discuss that when we will talking about the quantum algorithms. So the P gate changes phase by arbitrary phi. There are different variations of this qubit. It's like S gate, given by this graphical representation. It just flips the phase, so it's a pi over 2 gate. Okay, so if you substitute this phi to pi over 2, it will be equal to I. So that's I here. So yeah, and the result of this gate is just multiplying the state 1 by imaginary unit 1. And T gate, the one that we have in this circuit, here, 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 T gate. T gate is nothing but changing the phase by pi over 4. Sometimes it's also called pi over 8. Okay, so it's the same qubit. Phi is equal to pi over 4. So just like before, the result of this gate is multiplying the state 1 by this additional phase pi over 4. All right, so few words about the approaches or tools we will be using. The first one is a kind of kindergarten like quantum circuit simulator. It's a simple simulator that allows to, let me show you. So do you see my screen now? Welcome to this to Quirk.
Yes.
Yes.
Okay, awesome. Yeah, so it's a simple quantum circuit constructor. Here you can, so by default it starts from 2 qubits set in the 0 state. So we just discussed x qubit, h qubit, right? So you just pick and drag these qubits to, gates to the qubits. If you need more, you just create another one. And the result is shown here by these small block spheres. So let us start from state 0, right? And then when we apply this X gate, we're supposed to turn the qubit from state 0 to state 1, right? So this is indicated here. So we indeed get state 1. If we change by clicking this qubit 1, it will create state 0, plus returns to, doesn't change the thing, minus doesn't change, state I flips to minus I flips to I, and so on. So feel free to start playing with this constructor, but it's just for learning, right? So the purpose of this is just learning. More important is this tool, which is called IBM Q and Qiskit. Okay, so IBM is the company, electronic machines, right? Company that today in the avant-garde of quantum computing. This is the first company which started commercializing the quantum computers. They are today the most they have the most advanced quantum computers with the number of qubits of 1000. For the teaching, for learning, you're not having access to this 1000 qubit computers, but you have access to computers with a finite number of qubits, which is enough for our tasks. So Qiskit is the open source quantum computing framework. Framework means just library, right? Library written in Python and for Python. So from this Jupyter notebook, for example, you can write and execute quantum circuits, quantum algorithms without any problems. So very nice platform. I also should know that today we have much more such open source frameworks. There is one from Google. Google today invests a lot in machine learning, quantum machine learning. If you're interested, we can discuss that as well. And there are others. Qiskit, since it is established by the same company that provides access to quantum computers, so we'll be focusing on this one. So at this point, the like kind of the task to for you until the next week is to get yourself registered in this system. To do so, you just run this, click the link to get to the IBM Q, IBM Quantum. I already registered, so I just do sign to the platform, and this is my system. You will do that for the first time, then it will lead you to the registration page. Here I try to summarize like the steps you need to do to get yourself registered. The goal is to get this AP token. Okay, so for example, in my platform, I have this AP token, which is hidden, and I can copy it. And this AP token allow you to submit these computations to the remote, to the cloud backends, right? Backends here means, well, either quantum computer or the quantum computer simulator. All right, so here in this platform, we have the capability similar to this what's called Kirk, right? This Kirk. Here we have similar constructor. It's called composer. You run this composer and it leads you to this page. So here, similarly, you start from 2 qubits. Initially, qubit 0, qubit 1, initially in state 0, and then applying these gates like X gate, you see nicely. So from starting from 0 state, sorry, not from 0, but state 0, 0, because I have 2 gates, 2 qubits. Yeah, so now it's 1 qubit. If I apply X gate, it flips my qubit from state 0 to state 1, right? If I apply Hadamard gate, it will create the superposition, which is state 0, state 1. And this amplitude represents the probability, which is the probability amplitude square. Automatically, it writes you the code that you can execute. You can copy it and execute from your Jupyter notebook, or you can click this button here, set up and run, and basically choose the quantum computer you want to use, and then just run this circuit. We will do that later. So please get yourself registered and start practicing with this system. Again, here is the procedure, more or less. Okay. So we can divide or group all possible Qiskit simulations in 3 groups. The or types. The type 1 is ideal simulation, which means you have some circuit and you do the eigenstate simulation without any noise. Okay, so it's an ideal simulation. This type of simulation you can do on your local computer. You don't need to send this simulation to the IBM's backend, right? So you do this simulation in your computer. There is another type which is noisy simulation. This noisy simulation is kind of mimicking the quantum computer, including its unavoidable noise and so on. So you kind of mimic the quantum computer. The restriction, the natural restriction of these two is the complexity of your program. You can do this quantum computing sorry, quantum computing mimicking of quantum computing simulation for 5 qubits, for 10 qubits, maybe even for 50 qubits. You can mimic, you can simulate a quantum computer using, for example, 50 qubits, using your local or supercomputer. But if you will try to simulate something like 60 qubits, you will run out of memory and so on. So today's the most powerful supercomputers allow to simulate something like maybe 50, 60 qubits. But if you need to run something like hundreds or 1,000 qubits, you cannot simulate that using classical computer. You will need to use quantum computer. Which is the purpose for the third type of simulations? A remote backend. So remote backend means that you can use either a powerful computer to mimic quantum, including noise and so on, or using a realistic quantum computer. Okay, so we will be using this one, for example, in one of our next homeworks to simulate the circuit using classical analog of quantum computer and real quantum computer. So you, of course, probably don't have this Qiskit installed on your computer. To do so, you just run these codes: pip install Qiskit, pip install Qiskit Air. Qiskit Air is the simulator that allows to simulate either perfect or circuit with noise. Okay, and this guy just allow you to present the outputs in a nice LaTeX like format. Okay, so let us do some simple computations here for maybe 1 qubit. To do so, I import all these libraries from Qiskit. I import these circuits. I mean, some of them are not required for today. I just copy and paste this from my last year's lecture. So the first step you do, you create a quantum circuit, right, with a number of qubits. In this case, let us make this number of qubits to be 1. So this is the qubit created. By default, it's created in the state 0. So next, what us we need to add some gates, right? So let us start from Pauli X gate. I just run it, and since I use this name of the circuit, circ, this dot X means that I am adding this qubit to the circuit, and if I now draw the result, I see this gate in the circuit. To be able to see this in a more kind of nicely looking format, I can use this MPL option. So this is the gate, just like here. Oh well. So see the difference. The IBM Quantum uses this big plus in the circle to represent the X gate. By the way, if you need information about the gate, you just left click the gate and then you do information, and this information represents basically all you need to know about this gate. So it's a circle with plus, but in Qiskit returns this gate as the X in the rectangle. So then we need to simulate it. To do so, I import the state vector simulator from Qiskit Quantum Info. And we name the state, the initial state, our initial state in the state 0. And this number here represents the number of of amplitudes. So for a single qubit, it is 2 to the power of 1, which is 2. Right. So I create this initial state, and then I make this state to evolve using this function state.evolve and the name of our circuit. Okay. So I run this. It is very simple simulation, so it returns me, and I can see the result in the LaTeX format. So it's state 1, just what we expected, right? For the gate X, starting from 0, we get state 1, and quite often we can use another format which represents the state as a vector. Okay, so it's a state 0, 1. In the components, it is state 0, 1. In this Dirac notation, it is state ket vector 1. To draw a kind of a more complex circuit, I can, for example, put something like 4 here. It will be 4 qubits, 0, 1, 2, 3, 4, 1, 0, 0, 1, 2, 3. I can add some gates, for example, X to the first one, then Y to the second, Z to the third, H to the 1, 2, 1, 2, and then 3. Right. So running all of them at once. Unexpected index. Why it's so unexpected? 0, 1, 2, 3. 0, 1. Oh, okay, so it was extra space. Okay. So it was extra space here. Right, so let's run this one again. Then add these gates and visualize the result. So this is our set of 4 qubits with X, Y, Z, and H gates applied. So for now, this is these qubits are independent, right? They don't depend on the state of other qubits. To be able to make them dependent, state one depending on the state of the others, we need to use 2-qubit gates, the subject that we will discuss next time. All right, so again, now we start from state 0, meaning that all the states are initially in the state 0. And then, so how many qubits we have? 4, right? So it's 2 to the power of 4. This is initial state. And then we simulate the state and return the result. So this is the result of the simulation. It is the superposition of two elements, but in the matrix form, it is something like this. So it's a vector with 2 to the power of 4 elements, right? 2 to the power of 4 elements is 16. So it's a vector with 16 elements. Vector with 16 elements. All right, so this is pretty much it for today. This Jupyter notebook file will be distributed and shared with you, and the recording probably also will be provided for you. So let me stop the recording and then we can discuss.